Okay, everyone, good morning once again. So I released the marks from the second big class test to you just before Easter. The solutions, the questions and solutions, I've uploaded those onto Moodle now. So you can find those in that section in the class information for term 2. Okay, so I guess our focus now turns to the exam, which you've got in the last week of the exam period. Check the for that. So I thought today we could have a look at some more past exam questions. Yeah. So this isn't from any. This is from a good few years ago when it was a slightly different unit and stuff. But I think most of these questions on this sheet provide some good practice. For what you'll be facing. Okay, so we'll just have a look at some of the questions here. I'll just pick out some parts which I think are good. There's a couple of different types of questions here. As I go through it, please, if you have any questions at all, feel free to stop and ask for clarification. Okay, so let's have a look at this. So in question 2a, there's a number of small questions. Question 2 on my half of the course. In question 2a, you're given a definition of considering a sequence. The sequence is a sequence of terms an, where n goes from 1 to infinity. And the term an is defined to be this fraction 2n squared minus 1 times n plus 3 over n cubed minus 2. And it's fairly straightforward. You just are asked to determine whether or not this converges, and if so, find its limit. So our very first thought with this kind of a question should be the algebra of limits here. Okay. So we'll try and apply the algebra of limits here. So remember, the algebra of limits theorem allows you to do a few things. It allows you to say a limit of a sum is the sum of the limits, a limit of the product of the limits, a limit of quotient of the limits, as long as the other limits exist, of course. So what we've got here looks like a quotient, but we should maybe multiply at the top till we see precisely what it is. It's multiplying at the top, we would get 2n cubed plus 6n squared minus n minus 3. And we've got n cubed minus 2. So we got a good picture on the numerator and denominator. We'd be seeking now to apply the algebra of limits theorem, but we need a little bit of preparation for it, of course, because we can't. Oops, I forgot my second limit. We can't say the limit of this quotient is the quotient of the limits, because the individual limits of the top part and the limit of the second part don't exist. Both the top part and the second part tend to infinity as opposed to. So we do this trick to prepare it, is to express the same quantity but in this as a different fraction. So we divide above and below by n cubed here. It's still the same quantity, but it's represented differently as a fraction. And we can now see that the numerator consists of a constant 2 and a linear combination of various parts, but all of these subsequences are all convergent. because they're all a constant over some power of n, some positive power of n. And the same thing for the denominator, constant and a subsequent term which itself is convergent. So we can now apply the algebra limits here. Say that this is the limit at the top divided by the limit at the bottom. So that's by the algebra, by the quotient part. Quotient part of the algebra limits. And then each of those individual limits can be tackled with the linear combinations. Okay? Because bracket is a linear combination of terms. Bracket down there is the same. Okay? And well, just say that that's 2 over 1, i.e. 2. So that's by the linearity. Linearity part of the theorem. The algebra limits theorem, and the fact that 1 over n to the power a is going to go to 0 as n goes to infinity for all positive a. Okay. And each of those is 1 over a positive power of a. So the fact that we've been able to apply the algebra limits theorem to it at each stage, and we get a finite number out at the end, proves that this is convergent and has the limit. So therefore, and this sequence converges to the limit 2. Okay. So the things that someone marking that will be looking for is clear reference to the results, clear reference to the quotient part of the algebra limits theorem and the linearity part. Are you expecting to only just on a tour, right? Or smile nicely, some kind of visitor. Okay. Any questions about that tour? Okay. All right then, what do we have in part B of that? In part B, we have a little introduction. Everybody finish it up? Part B, a little introduction to a result about the geometric series. It tells us that the kth partial sum of the geometric series, the sum of AR to the n minus 1, is given by a certain formula. Explain how this is used to find the sum of the infinite series, the sum of this infinite series here. So it's giving us a lot of direction there. It's giving us a result about the geometric series and directing us to actually find the sum of the infinite series. But explain how this is used. So explain, like, this isn't the formula that tells you what the limit of a geometric series is. That's the formula for the partial sum. There's a little bit of actually, it isn't just a simple stick in the value parameters and get the answer. You do have to explain a little bit about the convergence of series here. Okay. So how would I approach this? Well, it asks us it's asking us for the sum of the series. So I begin a development of its quantity, the sum of the series. And what I'm first going to describe here is one of the key points that some of the marks will be going for here. The result in the question talks about the partial sum. Here I've got the whole complete sum, the whole infinite sum of the series. So what exactly is the link between those two quantities? Well, you should indicate this in your answer. The link between the two quantities is that the definition of the infinite sum, which is slightly conceptually problematic. I mean, how do you add an infinite number of things together? It seems a bit wrong when you think of adding as a mechanical time-based process, but it isn't necessarily, of course. It's a formal mathematical process. but we've given it a definition as the limit of a certain sequence. At this point, we've studied limits of sequences. We knew how to handle those. And the sequence we're talking about is the sequence of partial sums. Okay, so this, I mean, just indicate what we're quoting here. This is by the definition of infinite sums. Infinite sums or infinite series. Okay. So a good, clear presentation of that. Okay, and now we're sort of in a situation that we can apply the question. Okay. We can apply the result given in the question. You notice though that there's a slight twist to it. Is the result in the question, the way the geometric series is presented is with the summation index beginning at 1, n, but the exponent on the r being n minus 1. And here we do have the summation index n beginning at 1, but our exponent is n. So we just have to adjust it a little bit, just the way it's presented to us here. So we're going to separate off 1 at the third, so it's 2/3 times a third to the n minus 1. Yeah. But normally we wouldn't like unnecessarily expand the quantity like that, but we're doing it here so that we can present it in the same way. Yeah, present it in the same form as it is in the question. I mean, you don't necessarily have to take this down, but I'm just showing now how the form of what we've written there exactly mirrors the way the partial sum is presented in the question. So I can clearly see now that the value of the parameter a is 2/3 and the value of the parameter r is 1/3. So now I can apply the actual formula given for the partial sum, which is a, which is 2/3 times 1 minus r to the k, so 1 minus a third to the k, divided by 1 minus r, so divided by 2/3. Yeah, that makes sense. So that's by the formula. By the formula for sk in the question. So what can we do with this? Well, we could first of all simplify it. It's the same factor of 2/3 above and below the line. So just those. And this can be tackled with the algebra of limits theorem. There's no need to, there's no way, when you're just doing straightforward arithmetic, there's no need for a separate justification of it or anything. But here we can say we're applying the algebra of limits theorem. For the algebra of limits theorem. And finally this, now we can say it's just simply 1, because that quantity there, 1/3 to the power k, when you raise a number less than 1, a number between 0 or a number between -1 and 1, number with absolute value less than 1, when you raise it to positive powers, it's getting smaller. It's taking a smaller and smaller portion. As k goes to infinity, that of course is going to converge to third times a third times a third. So just kind of saying what you're getting there, saying that this goes to 0 as k goes to. So we've done what was asked. We've determined the value of the infinite sum. Sum on the left here is equal to 1. And again, think about what the person marking this is looking to see. They're looking for you to demonstrate your understanding. So the key thing that makes the link between the infinite series and the formula for the partial sum that's given in the question is quoting or presenting that definition of the sum of an infinite series. The infinite series is the limit of the partial sums. And just making sure you're treating the various indices and parameters correctly there. Okay. Is that okay? Any questions about that? Just you've maybe had a bit of time to look through the questions there. Is there any particular question that people would like to request that I do at the moment? Out of say the ones relating to my part, questions 2, 3, and 5, and 2, 3, 5, and 7. Any particular one that people would be interested in? There's no preference. I'll choose. Any requests? Okay, in that case, I might go on to question 7. This is a little bit different maybe to some of the ones that you've seen in other past papers. Question 7, this is from a good few years ago, but it's still more or less the same course. This is a question here about some of the treatment of functions. In part A, you're presented with 2 functions, and you're basically assessed on your understanding of the process of composition of functions. Part B is a question about the terms one-to-one and onto, injectivity and surjectivity. And C is a little application of L'Hopital's rule. Used to prove that limit sine x over x tends to 1 as x goes to infinity. And then part D is probably an application of that and harking back to algebra limits theorem as well. Okay, so let's see how we'd address these. So write down the definitions of the 2 composition functions f after g and g after f. Okay? So both f and g go r to r. F of x is defined as x squared plus 1. G of x is the exponential of 3x to the power of 3x. So both functions f after g and g after f are r to r. The only thing to be watching out for here is to make sure you calculate the 2 compositions correctly, and crucially that you get the order correct. Okay. So f after g, this function applied to x. Okay, you've got to remember that this is the definition. Okay, it's f after g. G is the function that's applied first to the argument x, then f is applied to the result of that. Okay. So this would be e to the 3x squared plus 1. Function g of x is e to the 3x. Function f of x is square the argument and add 1. So that's what we do. And we could express that then as e to the 6x plus 1. And make sure you handle exponents correctly. An exponent of an exponent, you multiply the 2 as well. Remember your rules of indices. Okay. And then the other one, g after f, applied to x. Well, that's g of f of x. So g of x is e to the 3 times its argument, and the argument here is f of x, which is x squared plus 1. Okay. So that will be e to the 3x squared plus 3. I mean, you could leave it like that, or maybe write it like this. to the e cubed times e to the 3x squared, maybe you factorize it as that. Okay, I mean, you find that you're getting into that stage as well. So we've composed them correctly, crucially got the order correct. And shown some of the development of it, not just jump straight to the final answer, but also shown the steps. Okay, any queries about anything related to that? Okay. So part B, write down definitions of one-to-one and onto for a function h, x to y. Prove the function g after f. This one is not one-to-one. Okay. So first of all, it's asking you to quote the definitions. You know, all the key definitions from the course we expect you to know. And it's asking you to quote them about a function h, x to y. So the function h, x to y is one-to-one, or injective, of the more technical sounding term for it, if, what's the definition? Well, the definition is that you never have two different arguments being sent to the same value. And a way that that's customarily presented is to say, we'll use our quantifiers for all x1 and x2 in the domain set X. If x1, if h of x1 equals h of x2, well, we just said injectivity says that that can't happen. You can't have two different elements of the same argument, same value. So it can only happen in the kind of strange case that x1 and x2 are actually the same value. They're not really two different values. X1 is actually the same argument as x2. Okay. So if the function h satisfies that condition, it means it can never send two distinct arguments to the same value. Because that would contradict that implication statement here. And this implication statement is quantified universally. That's for every x1 and x2 domain set. And then we do something similarly present the definition of onto. The function h is onto surjective if it's called onto. Onto means that the function kind of throws the domain onto the codomain, totally on top of the codomain. Every element in the codomain features as a value. The way of saying that would be for every element y in y, there exists at least one x in the domain such that h of x. That's not necessarily true for every function. When you say a function h goes from the codomain x to the codomain y, you're not saying that every element of y occurs as a value of the function. But when that does happen, that's what we call onto surjective. So you wouldn't, I mean, there are a few different ways of presenting the definition. You wouldn't necessarily have to write it out in a quantified formal statement like that. Just describe it precisely in English. I still get full marks. But the benefit of the logical quantifiers is it allows you to pin down very clearly. No ambiguity about what the definition is. So, and then illustrate one of these by showing that g after f is not one-to-one. So we consider g after f on x, and what was our nice expression for that? Is e to the 3x squared plus 3. It says prove it's not one-to-one. So The significant thing here is the squaring that's done with the argument x. And of course, you know that when you take a number, square it, you get exactly the same value as when you square the negative. Notice that you take g after f on 2, that's e to the 3 times 4 plus 3, or 3 times 2 squared plus 3, e to the 3 times 4 plus 3. But of course, that equally well can be written as 3 times the square of minus 2. Which is, of course, g after f applied to minus 2. So there are two distinct elements, 2 and minus 2, that both get sent to the same value, e to the power of 15. Now that, you can see how that explicitly violates this condition here. Because this condition says, well, if you do have two arguments whose values are equal, they must be the same element. But here you've got 2 and minus 2, which values are equal under the function, but 2 is not the same as minus 2. So that clearly shows that g after f is not 1-to-1. So that shows that g after f is not 1-to-1. In part C is assessing your knowledge and ability to carry out L'Hopital's rule. So it says, show how L'Hopital's rule can be used to prove that sine x over x converges to 1 as x goes to 2, as x goes to 2. So the issue, well, first of all, let's quote L'Hopital's rule clearly to show we know it. So we can say L'Hopital's rule says that if you've got two functions f of x and g of x, and both of them tend to 0 as x tends to infinity, so this is one of the things that L'Hopital's rule says, then the limit as x goes to, well, actually, it isn't necessarily infinity. As x goes to, as the argument x converges to any limiting value, and the limit as x converges to that limiting value of the quotient f of x over g of x. So that's something that you can't apply the algebra of limits theorem to. Okay? You can't say that limit is the limit of f divided by the limit of g, because those limits are both 0, and 0 divided by 0 is not defined. Okay? So L'Hopital's rule says that this is equal to the limit of the quotient of the derivatives, provided the limit of f prime x over g prime x exists. Just to explain the notation where f prime, g prime are the derivatives. Okay, so we quote L'Hopital's rule clearly again, and then applying this to the question, see that the limit as x approaches 0, sine x over x well, both of those functions approach approach 0. As x approaches 0, the sine of x is getting smaller and smaller, approaching 0. X is getting smaller and smaller, approaching 0. So we can differentiate the top and bottom. Well, the derivative of the top is cosine of x. The derivative of the bottom is just a constant 1. So that's the limit as x approaches 0. And cosine of x and cosine of x is a nice continuous function. So its limit is actually equal to its value at 0, and it just has the value. So that's done there as a little illustration of one of the ways in which L'Hopital's rule works. It's a little bit, to be honest, it's a little bit disingenuous that because we're using the fact that we know what the derivative of sine is in order to prove that result, but actually the true situation is the other way around. And the way you prove that the derivative of sine of x is cosine of x actually makes use of this result. So we're kind of doing things back to front. So this is actually something more kind of fundamental and should really be proved with a geometrical argument. It's an argument that doesn't rely on the derivative. But I mean, it's fine here. It's just a nice way to illustrate the use of the L'Hopital's rule. But really, the fact that sine x over x converges to 1 as x goes to 0 is used in the proof that the derivative of sine x is also. Okay, so then D, I think, is harking back to algebraic limits again. Use the results of part C, find the limit of this thing as x goes to 0. So the limit as x approaches 0 of 2x plus sine 3x over x. Yeah, so you just have to be a little bit careful with this. Of course, we break apart the fraction. You can break apart the fraction as 2 plus sine 3x over x. But just have to be a little bit careful in, okay, obviously the limit of the 2 part is just going to be 2. But what about the sine 3x over x? Remember, the result talks about the limit of sine of something divided by that same something. Now that's not quite what we see there. We've got sine of 3x divided by x. So the argument of the sine is 3x, but the denominator is just x. We need to make them the same in order to quote this result. So it's necessary, before we can apply the result of part C, it's necessary to rewrite this so that sine of 3x is divided by exactly the same quantity 3x. Because now it is sine of something divided by that same something. Something is converging to 0. The x is converging to 0, so the something is converging. Of course, this is no longer true now because I've just arbitrarily stuck a 3 in the denominator. So I have to compensate for that. So the fact that I've stuck a 3 in the denominator means I have to stick a factor of 3 in the numerator as well. And just change the quantity, change the way it's expressed. And not the quantity. So that's some preparation so that we can now get to applying the result of part C. Okay, so that's by the algebra limits theorem. Now we can quote the result of part C. So that's by part C. And just another little twist to explain here. It's presented slightly differently. It's the limit of sine of 3x over 3x. Not as 3x goes to 0, but as x goes to 0. But of course, as x goes to 0, so 3x goes to 0 too. Okay, so if you're taking the limit of this expression depending on 3x, as x goes to 0, that's the same as 3x going to 0. So then it's exactly, we can see it exactly as an instance of the result of part C, which is that. The limit of something going to 0, sine of something over the sum. Well, that's exactly what we have. So a place where you might have gone wrong there is, notice it is not correct to say, it wouldn't have been correct to say that the limit as x goes to 0, sine of 3x over x equals 1. Put it in quotes because it's not true. Okay. That would have been a misapplication of part C. Because it's not sine of something divided by the set of something. Okay. So that completes question 7. I might leave it there for this morning, unless there's any queries about that query. Okay, so just to say, so this is my last session seeing you in this unit, but I will be putting on an extra drop-in session for next week. I'll circulate an email about it, but I think it's going to be next Thursday between 2 and 4. I've set aside a room between 2 and 4 for just a consultation session if you want to come along with any queries or things you've been working on. And I continue to be available in my office. If you need to come and see me and ask me anything about the course, got any queries, do feel free to come and find me. If you're making a special trip in, email me first to set up a meeting just to be sure I'll be there. You're welcome to drop in as well. Okay? All the way to the exam. Okay, thanks for your attention.